In section 3.5 we're going to be looking at higher order derivatives. Higher order derivatives are used for curve sketching and for solving lots of different types of problems in calculus. Higher order derivatives are found by repeatedly differentiating a function. So for instance, we could have a function like f of x, which of course we also call y, and this would be called our zeroth derivative, meaning we have not taken a derivative of this function. Then we could look at taking successive derivatives like f prime of x. This would be equal to y prime, which would of course be equal to dy dx. These are all notations for the same thing. This would be called our first derivative. We'll go ahead and go up to a second derivative here. That would be f double prime of x, or y double prime, or d squared y dx squared. And these are all second derivatives. And of course our notations go up from here. Now one of the interesting things is once we get up to higher order derivatives, one of the notations that we use, instead of taking the fourth derivative and putting all these little slash marks up here, we actually skip to Roman numerals here. And so we'd go f, some people put 4 of x, and some people would put an IV of x. And all these mean how many derivatives we've taken from the original function. Now, what is the meaning of some of these? Well, the first derivative we know is the slope of the tangent line at any point along the graph. The second derivative, which is f double prime of course, is the rate of change of the derivative. So again, the first derivative was the rate of change of the function. The second derivative is the rate of change of the first derivative. So for instance, we could look at some graphs to help explain this. In this first graph, we can look at the first derivative and think about it as slopes of tangent lines. So our first derivative, in this particular case, the slopes of our tangent lines, if we kind of run them along here, we can say are always going to be positive. So the first derivative is always going to be greater than 0. Now what can we say about the second derivative? Well, the second derivative is the rate of change of the first derivative. So what we can see here is we have the rate of change in this particular case is slowing down, and then from here we can see that the slope is still increasing, but the rate of change of that derivative is increasing. So at this point A, something is important happening. So f double prime of x is negative for x values less than a, and we call this negative concavity. If you want to think about it as, can it hold water or not, or, a cave is concave versus convex. Now we also have past this point of a, f double prime of x is greater than 0. So this is for x greater than 0, I have positive concavity. And so this idea of concavity is going to be huge when we start talking about curve sketching. So that kind of gives you an idea of what the second derivative will do. Let's go ahead and look at a couple other graphs. On this first graph, let's go ahead and look at some slopes of tangent lines. The slopes of the tangent lines that we can look at here, we can see that we'll always have some sort of a negative sloping line. So in this particular case, f prime of x is less than 0. The slopes of the tangent lines are negative, so the derivative which gives us the slope of the tangent line will be 0. However, the rate of change of those tangent lines or of those slopes is positive, greater than 0. So I have positive concavity here. In this graph over here, I clearly have negative concavity, so my second derivative will be negative. My slopes of my tangent lines in this particular case are less than 0 as well. So what this is kind of showing is that we can have the same type of slope. So in this case we have negative sloping tangent lines. In this case we do as well, but the concavity can be different. So that's important to keep in mind. Positive concavity does not always go with positive sloping tangent lines and vice versa. Let's go ahead and look at some examples where we're taking higher order derivatives. The easiest thing to take higher order derivatives of are polynomial functions. That's because I can just repeatedly use the good old power rule. So let's go ahead and look at f of x equals x to the fifth minus 3x to the fourth plus 2x minus 1. Okay, first derivative. Like I said, good old power rule. Bring the 5 down, decrease the exponent by 1. Bring the 4 down, multiply it by the negative 3, decrease the exponent by 1. The derivative of 2x is 2, and the derivative of our constant 1 is just 0. So that would be the slope of the tangent line at anywhere along the graph. Let's go ahead and look at a second derivative. We have 20x cubed minus 36x squared, and the derivative of 2 is 0. Let's go ahead and look at a third derivative. 60x squared minus 72x. Okay, and you can see what's happening here is my powers are decreasing. Let's go ahead and go to a fourth derivative. 120x minus 72. And let's go ahead and look at a fifth derivative. When we're working with a polynomial expression, the derivative should eventually go to 0. And we can see that that does that in this particular case. On the sixth derivative, the derivative of a constant of 120 is 0 in this case. Now I kind of see some interesting things happening here. Let's go ahead and look at, let's start here with the third derivative. Let's look at this coefficient in front of each of these values. Okay, well, where did 60 come from? Well, 60 came from 5 times 4, okay, because I brought the 4 down, so I ended up with 5 times 4 times 3. So I have my 5 times 4 times 3 here, and that gives me my 60. Well, if you know anything about factorials, this is kind of looking like a factorial. Let's go ahead and look at 120. This is 5 times 4 times 3 times 2, which is 120. Okay, now here this is nothing new and exciting, particularly right here. This gives me that same repetitive value. And of course in here this value ends up eventually going towards 0. But this is kind of the one I want to focus on right here. Either of these. These are called factorials. And this pattern of factorials will end up being very important to be able to follow. So let's go ahead and talk about factorials for a second. Factorials are notated with an exclamation point. This doesn't mean you're really excited about n, it just means n factorial. The definition of n factorial is to take n and multiply it by the next lowest integer times the next lowest integer, etc., all the way until you get to 3 times 2 times 1. This never goes to 0 because as soon as you have a 0, the entire product would go to 0. So what ends up happening is when we have something like 3 factorial, that's 3 times 2 times 1, which is 6. 1 factorial is nice, it's just 1, and 0 factorial is defined to be 1. So these are some factorials that we'll see here, and you'll see this happening a lot when you take your products. You have a polynomial expression and you're taking higher order derivative, and those products end up occurring there. Let's go ahead and look at an example where we don't have a nice polynomial expression. In this case, let's go ahead and look at f of x equals the square root of x minus 1 over x. Now there's a couple things that we could do here. We know a product rule, so if we wanted to, we could actually rewrite this with a common denominator and flip it up top and use a product rule, or we could actually just use the quotient rule. But for now, let's go ahead and just rewrite this. So f of x would be x to the 1/2. I want to rewrite this in exponential notation, minus x to the negative 1. Now a question here is, as I take this derivative, will it ever end up at 0? The polynomial expression did when I successively took its derivatives, but will this expression? Well, first of all, this is not a polynomial expression. I don't have x's to nice integer powers, so these derivatives will never go to 0. So let's go ahead and look at taking this derivative. F prime of x. The derivative of this first piece was how we're going to start. So I bring the 1/2 down, decrease the exponent by 1. I bring the negative 1 down, decrease the exponent by 1. So rewriting, and I'm not going to simplify this, I just want to rewrite it, because if we simplify this, what ends up happening is I have to unsimplify it in order to take another derivative. I like my powers right where they're at, even though they're negative. So next, after I simplify, let's go ahead and take a second derivative. This would give us our rate of change of our first derivative. I bring the negative 1/2 down, decrease the exponent by 1. Bring the negative 2 down, decrease the exponent by 1. Now the trick on this one is make sure you remember you're decreasing. Let's go ahead and rewrite this a little bit. I have negative 1/4 x to the negative 3/2 minus 2x to the negative 3. So there's my second derivative. Now second derivative is going to give us information about concavity, as we've kind of looked at before when we get into curve sketching in the next chapter. Let's go ahead and take another derivative. Let's look at the third derivative. I have a negative 1/4 times a negative 3/2, x to the negative 5/2 when I decrease it by 1. Bring the negative 3 down, decrease the exponent by 1. So rewriting, for my third derivative, I end up with a positive 3/8 x to the negative 5/2 plus 6x to the negative 4. Now this continues on if we go to the fourth derivative, etc. But we kind of can see some patterns occurring here as I look through my derivatives. First of all, with my first derivative, my coefficient here was 1/2, and then it went to a negative 1/4, then it went to a positive 3/8. There's some patterns there. I have my powers of 2, 2, 4, 8. I have alternating signs, positive, negative, positive. And then this coefficient actually ends up being something like a product instead of like a factorial, and ends up being a product of odd values because I bring down the negative 3, the negative 5, the next step would be a negative 7, etc. So you just, when you take your higher order derivatives, you just keep taking derivatives. Now one of the most important applications of higher order derivatives has to do with position, velocity, and acceleration. Now the way this usually works is you have a position function. The position function, you might think, oh, that's p of t, p is position, but no, we use s of t to represent position function. Now if we take the derivative of the position function, I end up with velocity. We use v of t to represent velocity, and again, that's the first derivative of your position function. Change in position gives you velocity. Well, change in velocity gives you acceleration, which is a of t, which is the derivative of velocity, which is the second derivative of the position function. These are important. You definitely will want to know this progression. The derivative of position is velocity, the derivative of velocity is acceleration. Let's go ahead and look at an example where we can apply this. Okay, for this example, we're going to be looking at finding the acceleration at time t equals 5 minutes of a helicopter whose height is given by this position function h of t equals negative 3t cubed plus 400t. So this is a position function. Up above I said position function is usually notated with an s of t. This would be like if you were driving in a car and, like in a horizontal direction. The h of t is often used when we're looking at the heights of something, like if you threw a ball into the air, but it's not always going to be like that. So h of t in this case is given as position. So let's go ahead and look at velocity. Velocity is the derivative of the position function. And what we're going to want to do with this velocity is going to take another derivative of it in order to find something about acceleration. But in order to get to acceleration, we need to do velocity first. So my derivative here would be a negative 3, bring the 3 down, decrease the exponent by 1. The derivative of my linear term here, 400t, is just the linear coefficient. So let's go ahead and simplify. I get velocity is equal to negative 9 t squared plus 400. Next we want to get to acceleration. Acceleration is going to be the derivative of velocity, which is the second derivative of our position function in this case. Okay, let's go ahead and look at the derivative of velocity from here. Would be a negative 9, bring the 2 down, decrease the exponent by 1. The derivative of a constant is 0. So I get my acceleration function to be equal to negative 18t to the first. And of course the 1 is an implied one, so we don't need to worry about that too much. Now I want to know about the acceleration at t equal 5. So I will plug 5 in here. Negative 18 times 5 then is what I need to simplify, and I get negative 90. Now let's talk about units here. When I took the derivative of my position function, first of all, I'm going to have to assume I'm looking at height. Let's go ahead and look up here. Let's say our height is in feet. That'll help us determine our units. So when I'm looking at acceleration here, I'm looking at negative 90 feet per minute squared. That's the proper units here. Now what about the negative value? What does that mean in terms of acceleration? Does that mean you're speeding up, or does it mean that you're slowing down? Now if we looked at this graphically in Maple and looked at the position where we're at 5, that would kind of give us a good idea. So let's go ahead and open up a Maple graph. Let's go ahead and put in the position function. The position function is going to be a negative 3 times, I'm going to use an x in place of the t, negative 3x cubed plus 400x. I'm going to use x in place of t then. And that's our position function. So let's go ahead and make sure that that's what we think it is. Looks good. Now let's go ahead and plot this. So I'm going to right click. I'm actually using my stylus, so I'm going to click and hold. And let's go ahead and look at plots. Well, there's my plot. And if we look at what's going on at t equal 5, let's see if we can get in a good idea here of what's happening with this graph at t equal 5. Actually, let's go ahead and pull this into our journal document so I can write on it. That's kind of giving us an idea of what's going on at 5 minutes. Also, we'll notice that it looks like we have negative concavity here, so it makes sense that our derivative, our second derivative, is negative value as well. Let's go ahead and look at Galileo's formula. If you recall with Galileo's formula that we looked at in previous sections, we were given S of t is equal to S naught plus V naught t, kind of this is the general case, minus 16t squared. Well, what's going on with Galileo's formula is this value of S naught is called your initial position in feet. There's a different formula if you want to use meters. V naught is our initial velocity. And this would be given in feet per second. And then this value of t that we're looking at is the influence of gravity, and this t is equal to values in terms of seconds. So if you were given a problem in minutes and you were using Galileo's formula, you'd want to convert those minutes to seconds. So working with higher order derivatives is actually pretty easy and straightforward. If you have any questions, please let me know, but remember, the whole key is to successively take derivatives, and one of the ideas behind this, don't simplify in between because it gets more complicated sometimes, but sometimes we will be simplifying in the next chapter. Thank you.